Thank you. So, good evening, everyone. I'm going to present. I'm going to present. Still not audible. Speaker is off. Start. Speaker is off. Is off. Something. It's audible here, right? So here. And how is it possible? It is also I'm mute. Hello. Hello. No, it's audible here. It's coming from my laptop. Hello.
Yeah, I'm able to hear you. Yeah, please go ahead.
Hello.
We are able to hear you, Manali.
So I'll discuss our work on low complexity optimal policies for network control system. No, it's on. Hello. Hello. Yeah, it's coming, right? So in this work, in our work, we focus on wireless network control system, or in short, I'll call it as WNCS. So I'll briefly speak something about WNCS. So in WNCS, the components of this network system may not be physically co-located, and these components communicate with each other via wireless communication channels. So for example, let's say we have a plant. There's a sensor which observes this plant, and the sensor then sends this observation to a remote controller via a wireless communication channel. The remote controller estimates the state of the plant and generates control command based on its estimation. And then it sends the control command to an actuator via a wireless communication channel. The actuator in turn applies this control commands to the plant. So in a WNCS, basically it relies on efficient communication between these components, and we have to minimize the communication cost, also taken into picture the proper control of the plant. So now WNCS has many applications. For example, it is used in industrial automation to automate the process. It can also be used to monitor the traffic flow at traffic intersection, as well as in smart grid also. So now the motivation of our work comes from the fact that nowadays the transmission devices are usually battery operated, and each transmission is expensive and it consumes energy. So it may not be feasible or efficient to continually transmit or communicate with each component in the control system. So also continual transmission may lead to channel congestion, which may in turn flood the communication channel and lead to packet delays. So what motivates us is that we now want to minimize the communication cost, as well as to properly monitor the plant. So keeping in mind the challenges of WNCS, we considered three problems in our work. The first is a partially observed wireless communication channel, in which the sensor does not always observe the communication channel state. In the second problem, we consider a risk-sensitive cost objective. I'll explain what a risk-sensitive cost objective is in the upcoming slide. And in the final problem, we consider the case where the controller is a half duplex controller, which means that at each time, the controller can either receive a packet from the sensor, or it can transmit a packet to the controller, and it cannot simultaneously do both. So I'll first start with the first problem, in which we consider the problem of designing optimal scheduling policies for a partially observed channel. So in this setup, we have a source. This source is considered as an autoregressive process, which means that the source state at the next time step is a noisy function of the current source state. There is a sensor which observes this source process. We assume that the observations are noiseless. The sensor then encodes this observation into data packets, and then attempts a transmission of this data packets to a remote estimator via an unreliable communication channel. The decision of the sensor to attempt a transmission is denoted by 1, and the decision to not make any transmission is denoted by 0. The unreliability of the communication channel is modeled as a Gilbert-Eloi channel, which is a Markovian channel with two states. We say that the channel state is bad and denoted by 0 if any transmission attempt made by the sensor is unsuccessful, meaning that the packet is not received by the estimator. On the other hand, if the channel is in a good state, we denote it by 1, and it is in a good state if any transmission made by the sensor is successful, meaning that the estimator receives the packet sent by the sensor. Now, at each time t, the sensor, while making a decision at time t, does not know the channel state at time t. However, if there is a transmission attempt made by the sensor at, let's say, time 10, then the depending on whether the packet is received by the estimator or not, the estimator will send an acknowledgement signal to the sensor with a delay of 1 unit. So the sensor will know the channel state of time 11 at time 10 if it had made a transmission attempt at time. So now, so that's why we call that the channel state is partially observed by the sensor. Next, the estimator is fixed in our case, which means that the estimator at the estimate of the channel state at time t is same as the source state if the packet is received by the estimator. Otherwise, it is the source state parameter A times the previous estimate. The estimation error is the difference between the current source state and the current estimate. The transmission strategy which of the sensor is denoted as phi. Yeah, yes, sir.
So QT is 1, then in XT and the deliver channel is good. I will see XT badly. Deliver channel start, what happens?
If the Gilbert channel is bad, then nothing. I mean, no transmission attempt. It's no.
So that is so you're saying that that nothing is, so it's irrelevant.
It's yes.
So you understand, so what is CT you want to do? It's eraser channel or non-eraser channel. That's what
Yes. Yeah. Previous estimate, yes. So if the packet is not received, then it's the source state parameter times the previous estimate. Now our goal is to design an optimal dynamic scheduling of sensor packet transmission. So by dynamic scheduling of sensor packet transmission, we mean that the sensor at each time decides on whether to transmit or not transmit based on some state process parameters. So the state process parameter in our case, I'll discuss it in the next slide. And this is in contrast to continual transmission, where the sensor transmits at each time irrespective of the state process parameter. So dynamic scheduling, we mean that the sensor may attempt a transmission only when the state process exceeds a certain threshold. Otherwise, if the state process is within some threshold, then it may not attempt any transmission. So because of this, there's a trade-off between the communication cost and the estimation error. This is because if there is a frequent transmission of data packets from the sensor to the estimator, then it will reduce the estimation error, but it will also increase the communication cost. On the other hand, if the sensor does not attempt transmission much, then it will increase the estimation error while reducing the communication cost.
state process.
Yes, the state process in our case is the belief state of the channel. So it may be error, it may be belief. So we have
Here it's channel is very bad.
then
I ask channel is very good.
no, it's a belief of the channel being good. So if the belief is higher, then we'll attempt a transmission, and if the belief is less, then we won't attempt any
You
transmission.
want, but you speak like below the belief you're not.
Yes, actually, this is, I mean, the belief in our case, so this is in a general state process, it can be error also. So in our case, we have considered the state process to be belief. So yes, it's just a generalized. So making it more mathematical, we have to solve the problem in which we minimize the expected cumulative discounted square of estimation error while also minimizing the communication cost. So there have been work which dealt with Markovian communication channel. For example, there is a work by Ren et al. in the year 2017. In this work, they have considered the channel state to be instantaneously known to the sensor. And they have shown that the optimal transmission strategy of the sensor is threshold type with respect to error. So in their case, the state process is, for example, error. Next, there are works by Chakravarti and Mahajan in which they have considered the channel state to be perfectly known to the sensor, but with a delay of 1 unit. And here also they have shown that the optimal transmission strategy is of threshold type with respect to error. Now, in our work, we have neither considered the channel state to be instantaneously known to the sensor, nor we have considered that the channel state is perfectly known to the sensor with a delay of 1 unit. So what we have is that at each time, the sensor does not know the channel state. That's true. But the sensor knows the channel state with a delay of 1 unit only if it attempts transmission. Otherwise, it won't know the channel state. No. It got stuck. So we formulate our optimization problem as a partially observable Markov decision process. This is because the channel state is not known to the sensor when it makes a decision. We then use dynamic programming decomposition to solve the POMDP. Now, to ease our analysis, we have introduced the concept of folded POMDP, which I'll discuss in the upcoming slides. And finally, we have shown the existence of an optimal transmission strategy of the sensor, which is of threshold type with respect to belief state. So the belief state means the channel state estimate at each time. So for the POMDP formulation, the state consists of two components. The first is a belief state, which is the expectation of the channel state given the information till time t. The second is the error. The error in our case is the difference between the source state and the previous estimate of the source state. Now we are taking the previous estimate because of a time delay of 1 unit. So the sensor at each time does not know the estimate at that point in time. However, it knows the estimate of the source state with a delay of 1 unit. And that's why instead of the actual estimation error, we are taking an error, which is the difference of these two quantities. The control in our case is to attempt a transmission denoted by 1 or to not attempt a transmission, which is denoted by 0. This is the instantaneous cost, and now we have to minimize this POMDP, minimize the expected cost of this POMDP. So to make the problem more tractable, we have made two technical assumptions. The first is a stability assumption, which means that the source parameter A is strictly less than 1, and there is a positive probability of transitioning from the bad channel state to the good channel state. This is the first assumption. The second assumption is what is called positively correlated channel, which means that the probability of the channel entering the good state is higher if it is currently in the good state rather than if it is in the bad state. So I'll explain this positively correlated channel with an example. So let's say we consider the example of satellite communication. So in a satellite communication, the environmental condition affects the signal transmission. So let's say we have that if the environmental condition is bad or bad as in if it's cloudy or raining, then we say that the channel is in a bad state. Otherwise, if the sky is clear, we say that the channel is in a good state. Now, all we are assuming is that the probability that at the next time step, the environment has clear sky is more if at the current time step it is clear sky rather than if it has a cloudy sky. So the probability of switching from good to good is higher than switching from bad to good. So that's it. So now our main result states that states the structural property of the optimal transmission strategy. Specifically, we show that there exists a threshold type optimal strategy, meaning at each time the sensor attempts a transmission only if the current belief is greater than some threshold, and this threshold is a function of the error. So, which means that, let's say, at time t, we have this error. Now, corresponding to this error, we'll have a threshold on the belief, and the sensor will make a transmission attempt only if the belief is greater than this threshold. Otherwise, it won't make any transmission attempt.
Second condition doesn't work. Yes. Second condition doesn't work. You cannot show the.
Yes, yes, yes. Yes. So we use a multi-step approach. So in the first step, we start with showing that the value iteration can be used to solve the POMDP. Then we introduced folded POMDP because it is simpler to analyze. And to analyze this folded POMDP, we also show that this folded POMDP is actually equivalent to the original POMDP. Next, once we show this equivalence, we then come to the step of showing the existence of an optimal transmission strategy for the folded POMDP. Finally, we unfold the folded POMDP to the original POMDP so that the results of the folded POMDP also holds for the original POMDP. So this is the first step of value iteration. So the value iterate starts with an initial value of 0. And then at each step, we calculate the value iterates by taking a minimization over the Q value functions. The Q value function is the sum of the instantaneous cost and the expectation of the value iterates at the previous time step. We can show that this value iteration converges to the value function. The value function is the minimization of this expectation. We can also show that there exists an optimal strategy, which is stationary and deterministic. Next, before moving on to the construction of the folded POMDP, we first utilize a property of the original POMDP, which is the evenness property. And this property is instrumental in construction of this folded POMDP. So this property states that the value function and any optimal policy of the original POMDP are even in the error. So it can also be seen from this picture. Next, by exploiting this property, what we can do is that we can restrict our error of this folded POMDP to taking values only in the non-negative real line, which is in contrast to the original POMDP in which the error was taking the real values. So for the construction of the folded POMDP, we devise a new transition density function of the folded POMDP by modifying the transition density function of the original POMDP. Now to use this folded POMDP for our further analysis, we have shown that this folded POMDP is actually equivalent to the original POMDP, meaning the Q value function, the value function, and any optimal policy of the original POMDP actually matches with the folded POMDP when the error is non-negative. And hence, for our further analysis, we consider the folded POMDP. So coming to the main theorem, in this theorem, we show that the value function of the folded POMDP satisfies certain properties. The first property is that the value function is monotone in error, meaning that it is non-decreasing in the error. It is also non-increasing in the belief state. And finally, we show that there exists a threshold such that the sensor attempts and transmission if the belief exceeds this threshold. show this properties using forward induction method, but a crucial step is to show that this threshold structure exists. So I'll explain this step C in much more detail. So this is the proof of step C. So first, for this, we first show that the Q value function is concave in the belief state when the action is 0. We then show that the Q value function is linear in B when the action is 1. Then third, we show that it is optimal to not transmit when the belief is 0, which means that the Q value function of the action 0 is less than the Q value function when the action is 1 for the case when the belief is 0. And then we have two more cases left. So we start with the first case, considering that it is optimal to transmit when the belief is 1, which means that the Q value function for decision 1 is less than the Q value function for decision 0 when the action when the belief state is 1. So let's look at it more visually. So yes, so we have this concavity property, which is the first property. Then we have this linearity property, which is the second case. We have also included the third case here. As we can see, when the belief is 0, the Q value function for action 0 is less than the Q value function for action 1. And the fourth case is also included. So when the belief is 1, the Q value function for action 1 is taken to be 0. It is taken to be less than the Q value function when the action is 0. So this, so as we can see, there's an intersection, and this intersection is what is the threshold on belief. So if the belief value is greater than this threshold, then it is optimal to transmit because the Q value are less in this case. And if the belief is less than this threshold, then it is optimal to not transmit because the Q values are lower in this case. And coming to the second case, we consider the case when it is optimal to not transmit even when the belief is 1. And in this case, for all values of belief, it is optimal to not transmit. So this shows the threshold structure of the transmission strategy. And then finally, the unfolding step, we can unfold this folded form DP by using the evenness property and the equivalence property. And the value function can be shown to be non-decreasing in magnitude of error. It can be shown to be non-increasing in belief. And finally, there exists a threshold structure of the optimal policy. So to validate our theoretical results, we have set up the discount factor 2.99, transmission price to be 0.65. The air process parameter is 0.7. The noise is normally distributed. These are the channel parameters. So this graph has already been discussed. So the value function is even in E, non-decreasing in magnitude of error. It is non-increasing in belief. This is the optimal transmission strategy. We have also considered we have also compared the performance of our optimal policy with an IID policy. So we can see that the cost of this optimal policy is less than this IID policy for all values of P, probability P. So we say that the optimal policy outperforms this IID policy. We have also compared the performance of the optimal policy with the IID policy by changing the state parameters. And in all the cases, it can be seen that the optimal policy outperforms this IID policy. As an extension to our this work, we have also included the case of joint optimality. So in the previous work, we had made the estimator to be fixed. Now we are jointly optimizing the estimator as well as the sensor strategy. So this is a decentralized problem, the sense that there are two decision makers and the information available to both of these decision makers are different. So we have shown that the estimator of this kind and the threshold strategy of the sensor are optimal, are jointly optimal. Next, coming to the risk sensitive problem, the setup is almost similar, except the case that here we consider the channel state to be perfectly observed by the sensor, which means that the sensor at each time step knows the state of the Gilbert-Elliott channel. The main difference is in the cost structure. So here we are dealing with a problem in which we have to minimize the expectation of this exponential cost. This is in contrast to the risk neutral case in which we only had to minimize the expectation of this cost. There was no exponential term. So the main advantage of this type of cost is that because of this exponential term, it penalizes the higher order moments of cost. So if there is an adversary which is resulting in change in parameter of the system, then in that case, this risk sensitive optimal policy will be more robust to variation, which means that the optimal policy in this case will not change much in contrast to the risk neutral one. Yeah. Which one? This. Channel state, yeah, as in the estimate, because we have seen that. That's okay. I have to go at the point. So actually, the delay in which the channel, we have considered the state to be the belief state, which means that if there is even if there is a delay, we will only consider the threshold structure to depend on what our depend on believing how good the channel state is at the current state. So all the information, yeah. So when we take the belief, so it is the expectation of the so it is the expectation of the channel state depending on all the information. So the information, this FT, it consists of all the things that sensor knows, including the delay of the channel state. So with no, the delay is only one step. So what we're doing is that, let's say we know that at the previous time step, the channel was in a good state. Now, using that information, we can calculate this belief depending on the probabilities of the Gilbert-Elliott channel. So let's say at time t minus 1, the sensor has information that at time t minus 1, my channel was in one state, good state. Now, using the channel probabilities, I can estimate this belief. So it can estimate, okay, if it was in the good state, then with P11 probability, it will be in the good state in this time step also. Or if it was in the bad state, then it can expect the channel to move into a good state with a probability of P01, which is this. So using that information, since if UT is 1, then I know the channel state perfectly. So using that information, it can actually model the values of the belief. So that I did not write the values of the belief explicitly. We can calculate the values of the belief explicitly depending on the information it has. And what about the error? Error, it's non-decreasing in error and non-increasing in belief. So it's, yes, yeah, this one. So it's basically non-decreasing in, increasing in error, and it's decreasing in belief. Okay. So coming to the risk sensitive part, the main challenge in risk sensitive costs is that in contrast to the risk neutral case in which for infinite horizon we have a stationary policy, in risk sensitive cost, there might not admit any stationary policy if the cost horizon is infinite. Also, because of the multiplicative nature of the cost function, the policy may depend on the history. So now, basically, we start with a finite horizon problem so as to remove this challenge. Next, we show the existence of optimal deterministic Markov policy. So because of this existence of this Markov policy, the policy will now depend only on the current state. We then introduce a folded POMDP, and finally, we establish a structural result for the optimal scheduling policy, meaning that we show that the optimal scheduling policy is threshold with respect to the error. So the error is similar to the previous setup. The channel state, we have the state process consisting of channel state. The control decision is either to transmit or to not transmit, and we have to solve this MDP. So in this setup, we show that there exists a threshold type optimal strategy, meaning that at each time the sensor decides to transmit only if the magnitude of error exceeds a certain threshold. So we show that specifically that if the channel is in a good state, then the sensor transmits only if the error exceeds some threshold. And if the channel is not good, then we do not attempt any transmission. So we also use value iteration here to solve the MDP, and then similarly we construct a folded MDP, and we show the structure of this optimal strategy for the folded MDP, and finally we unfold these results. So here the main thing is to notice is that the value iterates here are multiplicative in nature, which is in contrast to the risk neutral case in which we had an additive cost. So here the Q value function is the exponential of the instantaneous cost times the expectation of the previous value iterate. And finally, we can show that there exists an optimal transmission strategy, which is Markovian, meaning it only depends on the current state process. And after constructing the folded POMDP, we first show the existence of the threshold policy for this folded POMDP, and then we unfold these results. I'll move on to the third problem in which we have a half duplex controller. So here I'll explain the setup. So we have a plant, and the sensor is battery operated, so with a limited battery capacity. The sensor observes this plant, and the observations are assumed to be noiseless. It then transmits this observation to a remote controller via an uplink channel. The controller estimates the plant state depending on the observation sent by the sensor, and then it generates control commands. These control commands are then sent to the actuator via a downlink channel. The actuator then applies this control to the plant. So the uplink as well as the downlink channel in this setup is considered as an IID channel, which means that at each time there is a probability P that the packet is being dropped. The estimator is fixed. So the controller in this case is a half duplex controller, which means that at each time the controller can either receive a packet from the sensor or it can transmit a packet to the actuator, but it cannot do both simultaneously. So the main trade-off is between the plant state estimation and timely control of the plant. So this is because if, let's say, there is a frequent transmission of sensor packets from sensor to controller, then this will improve the estimate of the plant state. And as a result, it will improve the control command generated by the controller. But it won't be able to send these control commands to the actuator, which may result in bad control of the plant. On the other hand, if the downlink channel is activated frequently, then although the actuator will have a timely control of the plant, but the quality of this control commands generated will degrade. So our optimization problem here is to minimize the expected discounted square of the state process. We formulate it as an infinite horizon problem. We formulate this infinite horizon problem as an MDP. Identify dynamic programming decomposition, and finally show the existence of a low complexity optimal policy. The state here consists of 4 components. The first is the plant state. The second is the age of the packet which is available at the controller. The third is whether a control packet is available at the controller or not. And the fourth one is the energy level of the sensor battery. There are now 3 decisions that can be taken by the sensor. So the decision maker here is the sensor itself. So the sensor may take a decision to not activate any of this channel. The sensor, which is denoted by 0, the sensor may decide to activate the uplink channel, which we denote it as 1. And third, the sensor may decide to activate the downlink channel, which we denote as 2. The instantaneous cost is x square. And okay. Now we make 2 assumptions. The first assumption is one-step controllable assumption, which means that in the absence of noise, the controller will drive the plant to 0. So that is one-step controllable assumption. And the finiteness assumption states that there exists at least a policy such that the expectation of this cumulative discounted cost is finite. Now coming to the main result, we show that if there is a control packet available with the controller, then the downlink channel is activated, which downlink channel is the channel between the controller and the actuator. So that channel is activated only when the magnitude of the state increases a certain threshold. And this threshold depends on the age of the packet available to the controller and the battery energy level of the sensor. So to conclude, we considered 3 setups, and the problem was to minimize the cumulative expected cost under various assumptions on communication channel and system parameters. We posed these problems as POMDP or MDP as required. And then we constructed simpler folded POMDP, which eases our analysis. And finally, we derived low complexity policies for this setup. Thank you. Thank you, Manali, for an informative talk. Are there any questions? Yes, yes. Similar to folded or POMDP. Similar to folding. I have to look. I think there might be. I don't know. I have to look. We implemented only. I mean, we use only simulation. We did not implement it practically. Thank the speaker again.